The broadcast is now starting. All attendees are in listen-only mode.
Good evening, everyone. Welcome to this webinar. We will start in a couple of minutes. Thank you for waiting. Okay, I think we can start. So welcome again to this webinar. Will be about complex material model, nonlinear material model in SIMULIA Structural Professional Engineer. I'm Alessandro Bellini. I'm the Euromed Senior Territory Technical Manager. Euromed means basically Balkans, Italy, Israel, and Turkey as well. I'm the simulation specialist and I'm your host for today. As usual, the webinar is being recorded, so you will receive a link in a couple of days to review the webinar if the line is not so good and so on. We are using GoToWebinar platform, so you can input your question in time you have. Also, I provided to you some PDF with additional documentation about the material models that we will see today. So you can click on the handout portion of the GoToWebinar. You can download the PDF. They are provided to you as they are. I've just collected some of them on internet, so it's not something official from us. So let's talk about the agenda. We will check what is a nonlinear analysis in a moment, and I will talk about plasticity model, for example, in metals, in steel structures, and so on. We will then discuss about hyperelastic models, especially useful for rubber-like materials, for sealing materials, and so on. We will see briefly the creep model and the damage model. Let's say the damage model means also that the mesh inside the analysis can be broken. So we will see something interesting about that. And in the end, the question and answer session. So let's start talking about SolidWorks simulation. Now we are expanding its scope with SIMULIA family on 3D experience. So we are starting with the first piece of application that is Structural Professional Engineer, and more that will come. So this is just a nonlinear static analysis, but we will see also in the future dynamic and explicit analysis. And I repeat, on the 3D experience platform. Here, the needs of the companies are, of course, the needs of analyzing more complex physics, so multi-physics on a larger scale. So it it means on very large assembly or with very large models and so on. Also, computer resources are needed here because we cannot rely anymore on a single computer or just on our computer. We want, you want to use also remote computing as well. So our servers, our Dassault system servers, access, flexibility of access. So it means what I need when I need it. So basically, a lot more flexibility related to the actual business model. Easy of use, of course. We are used to have SolidWorks. It's a nice and clean interface. It's very easy to use, and we have the same need for the future. So 3D experience is the solution with the SIMULIA technology that is leveraging Abacus solver, especially in nonlinear multiphysics, cloud computing again on our servers. So here, imagine to rely on the Dassault system server to analyze on 32 cores for analysis. And so you can go on your PC, on your tablet, you can go on to design something else. You are free to use your PC while our servers are running the simulation, are solving the simulation. The subscription model here is essential. You want to use a very high level of analysis when you need it. You don't want to acquire it and let's say make it unutilized in some moments. You want to just use them when you need it. Also, an integrated workflow. What does it mean? In SolidWorks, we have a connector that is the simulation connector that is transferring all the models to the 3D experience, all the boundary condition and the materials. Also, it's more easy to collaborate using a platform because it's already in the web, on internet, on the cloud. So it's another step towards collaboration. If you want to understand more about SIMULIA Simulation Engineer, is the formal name. Now it's a Structural Professional Engineer. You can rely to my channel on gotostage.com/channel/Alessandro Bellini. You can find the webinar on SIMULIA, and you can register and review whenever you want. So now I would like to ask you the first survey. So in your company, if you are using physical prototypes for evaluating products, if you are not using, or if you are using only for main products or for all products. Please vote. I will wait some seconds here. Okay. I'll try to reach 80% of you. Okay. So let's close the poll and I share it. So 50% of you are not using physical prototypes and 50% are using only for main products. Okay, thank you for the poll. So the second poll here is about simulation. If you are using already SolidWorks products wherever or other simulation software, or you are not using any simulation software. So again, I will wait some seconds. Please vote. Okay. Okay, so I'm not reaching everyone, but okay, we can go on. So most of you are using already SolidWorks products. Okay, so let's talk about a nonlinear system. So basically, it's a system where there is a relationship with between force and displacement. When we are analyzing a normal system, let's say a simple system, basically in a linear fashion, when you apply a force, you get a displacement, and when you are applying double the force, you get double the displacement. So basically, that is a linear system. In a non-linear system, this relationship is no more. So basically, it's a much more complex situation when you have something that is not behaving, let's say, in a very simple way. So, for example, the types of nonlinearities involves geometric nonlinearities. So, I mean, for example, for buckling, so some profiles tends to bend in a very quick way, and this is not linear, of course. We are talking about this webinar about materials. So in this case, basically, we will see how to model materials, complex materials inside the simulation. And of course, we can talk about contacts in a nonlinear problem. But this is out of this webinar. You can rely again on the last webinars I have already produced on SIMULIA. So let's talk about the nonlinear material models. These are some examples of the models I will explain with this webinar. Plasticity, it's very important model, and it's very important effect that you want to understand. So basically, you have a displacement or a force that is producing a strain in the material that is permanent. Basically, if you are removing the force or the load, you will see a permanent displacement, a permanent deformation of the component. So we need to understand, and we need to use a plasticity model here, and we will see something about that in a moment. Hyperelasticity, we are talking here about polymers, rubbers, sealing. So basically, all these kind of material that are really stretching a lot. We are talking about more than 300% of the normal, of the, let's say, the normal measure, the normal dimension. So in this case, we need a specific model to take into account this large deformation in the material. Creep is about the time. So it's an effect that with the time occurs on material like, again, rubber, but also metal and also human skin, for example. So the strain rate, it's very important here. Also, the time that you apply the load and you are remaining, you are, let's say, tensioning the material. So creep is very related to the time. It's also it's related to high temperature in the model, in the material. Anisotropic means that we have different materials like wood or thermoplastic with fibers or composites. So different materials that have different behavior in the three-dimensional coordinates. So basically, they have laminas on their materials, and we have to use a specific model for anisotropic or orthotropic materials. For example, we can take a linear spring. Just for starting, this is a normal spring that maybe you are using. So F in this case is related to X with this constant that is the K constant. And this is a linear approach. So again, if I'm doubling the force, I can get double the distance. In a nonlinear spring, you don't know anymore which is the K as a constant, but you have a curve instead. So you need to understand which is the this curve related to the material, because otherwise you will not be able to predict and to analyze the material. So this is an example this is an example of the stress strain curve of a material. Typically, this is for metals, for aluminium, for steel, and so on. So you have here, a elastic behavior in the first phase, and then a yield point. So the yielding then delineates the end of the elastic behavior. So after the yield, basically, if you load again if you continue to load the model and then you come back, basically you will follow another path. So you will get a permanent deformation. Here you can see on the strain. So this is a plasticity. This is an effect that you want to understand. How to do that? Basically, you need, in this case, more points above the yield stress in the plastic zone. So here you need, in the model related to SIMULIA, of course you need the standard properties as density, as elastic modulus, and so on, but you also need this part of the curve. So you need those points with yield stresses versus plastic strain. So those are easily obtainable by the uniaxial stress on materials like metal, and you have to input in the software to take into account the plasticity in analysis. Just for example, as a plasticity demonstration here, I have a bending machine. This is a bending machine that bends profiles of aluminium and so on. You can see the rotation in the first step of 180 degrees, and then the release, and it happens, of course, that the plasticity inside the material has bended already the profile, and so I can see which is the results of the bending. Here I have multiple contacts just ended by the general contact. You will see this in one of the previous webinars that I've already done. A mixed mesh with X and hexaedrical and tetrahedral elements, and high precision just with the default dimension, and a multi-step approach. That means that I can easily identify a step, for example, in this case of 180 degrees in a direction, and then a second step in the opposite direction, and that's it. It's very simple to define. And of course, it's very, very fast. We can see in a moment here, I'm just importing the SolidWorks files into the experience. I'm using here the structural model to prepare the model and the mesh. Here it's very simple to define an hexaedrical mesh on the profile, another one on this block, very easy, and then a tetrahedral mesh of the second order onto the main part that is rotating the profile. Here also I'm defining a tie that is the link to, let's say, to define like a press on those two surfaces. Here I can select a material from the library, and you can see it's already with plasticity behavior enabled. Then, of course, I can define the boundary condition here, very simple. I can apply a rotation to the center of this coupling of 180 degrees. And this is the first step. And in the second step, I can just revert it back very easy. So I can define another step. It's another static step. So the first one is going to run from 0 to 1 second, and the second one from 1 to 2 seconds. So here is the second step. So again, I can define the time increment and so on. And now I have just to define the general content. Here it's very simple because with one feature I can define all the content that will happen in the model, just with this single feature. And I can define, of course, the friction. So let's also run into the cloud. Here I can use the maximum speed of the cloud, and in a very short time, here it solves in 30 minutes. I can see the results. Those are the displacement of the profile, so I can see the bending and then the release of the profile. Here I can see the plastic strain. So here I can identify which are the zones that are deforming permanently. And here I can see also the zone that instantaneously are yielding. And so I can have a feedback, a visual feedback on the plasticity model itself, and also on the elastic return that is very small, but I have to identify it, and the contact pressure. So let's talk about now the hyperelastic models. Here we are taking into account material like neoprene, natural rubber, silicone, and so on. In this case, what is the usual activity is to define three laboratory tests that are the simple tension, like the uniaxial tension is very similar, a planar tension that in reality is to calculate the shear, and the biaxial extension that is basically on two axes on a plane. So with those three curves, we have defined the material, but then we have to input this kind of things into a model. To understand the model, now I'm introducing the Mooney-Riving model. Here I have a polynomial approach that is called the strain energy potential, and I have here the general formula in the middle, and a special formulation that is n equals 1, that is the Mooney-Riving model simplified, with just C10, C01, and D1. Think about these kind of curves. Now we have to define which are the constants in this polynomial model. So to do that, we have also to make it, let's say, inside the curve with a special program. We will see in a moment. To understand better here the model that we can use in SIMULIA, we can see that we can use a lot of other models for hyperelastic materials. So we have Ogden, but also we have a general polynomial approach. We have Mooney-Riving and others. Let's say the best in this situation are Ogden and Mooney-Riving. But of course you can use other model if you have the constants. Here you can see an example of a generic rubber with C10, C01, and D1. So you can see those two constants are defined in the model, and D1 it's a compressibility constant. It's optional. You can set it as 0 if you want a perfectly incompressible rubber, or you can set it very, very small, as in this example, it's 3.6 at the minus 0.08. And in this model, in this case, I can use this model to analyze this structure. So if you want, you can go further, and you can see in this example, we can use the n equal 2 in the polynomial model. I can go back just a moment here. So here you can see that I can refer to the general polynomial equation, but I can resolve for more let's say for all CEJ, and you will end up with 5 constants here. So the polynomial model here, Mooney-Rivlin at the power of 2, it's C10, C01, C20, C11, C02, plus 2 compressible constants. Here again, the compressible constants D1 and D2 are optional. The first one is, as before, is linear, and D2 it's on the power of the second order. So the question is how to work out which are the constants for your model given the curves. You need some type of software. Here is just an example. I'm not supporting any specific software. You can use also Excel if you want. So in this case, I have the curve, and the software is trying to fit with varying the constants in the model. In this case, the EO model is varying the curve, so I can see the blue curve, that is the model calculated from the constants, if it fits with the real data that I have in red. So if it's match, or very similar, it's match the curve, I can use those constants into the software. Okay, so it's not an easy task, but it's a process that you can take. Also, I've talked about Ogden model. It's another way to represent a rubber in a hyperelastic material. It's based on a similar approach on the strain, elastic strain energy, but here we are referring to alpha 1, 2, and 3 that are the tensor, the deformation tensor of Cauchy-Green. So here, what you need instead of CEJ, you have to calculate mu1 and alpha, mu-E and alpha E. So basically, in this case, you need constants again to calculate the model, and it's the same approach that we saw before. Also here, you can define which is the power of the model. Basically, with n equals 1, you will have just 2 constants, mu1 and alpha 1, and then you can grow with the model. Of course, more constant you are using, and more detailed, more precise is the model. Here in example is an example of a rubber bumper stretched with a flat part. So you can see the deformation. You can see also the self contact of the part. You can see, of course, the pressure and the stresses that arise in the part. So this is just an example of a complex shape and a complex material to analyze. Also, I provided a more complex situation because I removed some of the boundary condition. And here you can see that it's not more symmetrical, and on the base you can see the face is not more retained. So you can see one portion that is leading on one side, and then there is a self-contact to stabilize, that is stabilizing the situation, the part. And then you can see again here the flat part on the bottom is leveraging, is going up. So it's much more complex situation. And for example, here I have used the Ogden model that is much more robust of the Mooney-Rivlin. A special case of hyperelastic materials, it's called Hyperfoam. Hyperfoam has a similar curve, a stress-strain curve like we saw before for the hyperelastic materials, but there is a little bit difference in which is the compressive force is taken into account. Similarly, this is for rubber-like material, but also with a high compression. In this case, the point is the high compression instead of large deformation in general. It's ideal for foam, for polyurethane, for latex, and so on. Basically, if you are seeking large deformation, large displacement, and if you want to take into account contact pressure, if you want the results of the contact pressure over human body, for example, mattresses, cushions, chairs, sofas, and so on. Here, again, we have a polynomial model specifically for Hyperfoam. You can see I've identified mu1, alpha 1, mu2, and alpha 2. We can also use, again, here, optionally, mu1 and mu2, the Poisson ratio, and it's in this case, I've used it as 0. It's not used. In this case, I have a block, again, with the symmetry. You can see the constants of the Hyperfoam model here. And there is a compression of this kind of part on the top. And I can see the displacement. And all the contact is already defined with just the general contact. Here, again, I can see the displacement, the contact, and this kind of sliding on the back, on the bottom. Here the contact with the stamp, and so on. Let's talk now about the creep model. The creep is a permanent deformation, but under a static load, so it's related to a time. So if I apply a load, for example, in this tube, in this pipe portion, I've applied a pressure of 14 megapascal, but also it's related to an elevated temperature, to high temperature. So in this case, 540 Celsius degrees. So it's another effect that you have to take into account if you're using this kind of a situation, very critical for a metal part. So in this case, I've defined a static and a quasi-static step to define the pressure load, and then I've run the simulation with the creep model. To use the creep model, of course, we need to input a very long time in the simulation, not seconds, but here we are using a total time of 50 years. So it's very interesting. I can rely on the software to understand if it will last so long. Also, the time increment here it's 1 hour. So I will have a calculation each and every hour in the simulation. Here, of course, I have the model, and the creep law is defined with a lot of options. Let's say you can use a lot of model, and the most used is the strain hardening here, and it's a power law. The power law is a similar curve to what we have saw before. And again, here you need the test data, and you need to fit the data, for example, in Excel or with other software. If you have done the analysis of the creep, you will end up with the results about equivalent creep strain. This is the most important thing that you want to know. So basically, here I'm defining which is the portion that is straining due to the creep. Okay, so this is very important at the end of the creep analysis. Now let's talk about the damage models. Here we are taking into account the real, let's say, realistic damage that can occur to a material. We saw earlier in the plasticity model, we have analyzed, we have the stress strain curve, we have analyzed the elastic portion, we have the plastic portion. Now, from the point A, we have to define which is the starting point for the deterioration of the material, for the destructive part of this curve. So we want to analyze from A to B. And in this case, we need, first of all, the damage initiation model that is occur in point A. Then we need a damage evolution model, because we need to understand how it's the evolution of the damage that occurs from A to B. And we need to understand, we need to define how the element in the mesh will be removed. So this is a very complex approach, very powerful. Also, here, very realistic. We are seeing what is happening in reality. So we see also the removal of the mesh, of some portion of the mesh. The damage initiation criteria, now I will talk about only for ductile metals, for ductile damage model. We have a lot of other models, but here is the only one that for the moment we can use in SIMULIA Structural Professional Engineer. The other one can be used in the explicit dynamics. So in the ductile initiation criteria, basically we are taking into account the fact that the damage is triggered by voids, by creating voids. Basically, there are a lot of microscopic voids that are growing because of the stress here. So you can see in the image on the top. So these kind of voids are enlarging and are aggregating, and then they are separating the two portions of the metal. Here, the ductile criterion is triggering, of course, the damage initiation, and it's based on the stress triaxiality. Triaxiality means that we are using P1 plus P2 plus P3 divided by the strain rate. So in this case, we can also use more curves, depends on the strain rate. So the let's say the velocity that we have applied to the uniaxial test. Okay, usually we have one strain rate, but we can also use more of this. And in the model, you can see in the damage model of SIMULIA, we can use a lot of other models rather than ductile metals. But again, I will focus for this webinar on the ductile damage. I've used also the Johnson-Cook damage, that it's very, very interesting. Again, it's a power law model, but here I will focus on the ductile damage. So here you can see fracture strain is the strain that we have on the model related to stress triaxiality based on a specific strain rate. We have talked about the damage initiation, and now we have to talk about the damage evolution. So once the damage is initiated, we need to address how it's tracked for each and every element. So we need, in this case, a combination of all the effects that are active, maybe more than one, and we need to capture this on a variable that is called D, the damage, for each element. So if the damage is equal 1, we will have a stress that is basically removing that element. Sorry. So in the damage evolution, we can use let's say basically two ways. Here you can see the energy-based damage evolution, linear or exponential, and again this is a power law model, or just the displacement-based damage. So here we will use just which is the displacement that is starting to damage the element. And here you will see the evolution of the damage. So again, we are starting from A, that now it's D equals 0. That is the end of the plasticity curve. Now we want to understand more of this curve, so we are using this portion above, and we are going to soften the material. Because why softening? Because we are checking for voids into the material. So basically the material is softening itself, and then we will release in a void, and the two portions near the void will break, will fall apart. So here is the example. This is just the uniaxial stress test. As you know, in the reality, you can see now the necking phase on the test, and in a moment you will see the break. Now we can see also the break of the test. Again, here I've not applied a very fine mesh because I want to stress let's say to focus on the stress, and you can see the element removal when the final phase the portion of the material is breaking in the middle. Also here it's very interesting because you can of course find useful information from the simulation itself. You can also plot, you will see in a moment. We can see which are the elements that are hidden because of the removal, because the damage was 1, so that element are this is the starting of the damage, and you can see it's in the middle. Imagine this is a double symmetry setup, so imagine this is the internally to the component, to the portion of the part. So basically here you can see in the middle it's creating the void and then it expands. And here also you can see the real damage curve. As we saw before, the elastic portion plotted on some of the points near the breaking point. So here you can see the elastic portion, you can see the plastic portion up above, and then the release of the damage, so the third portion that is going down, and finally the break of the portion of the material. This is a video about Sharpie impact. The Sharpie impact is about this kind of test to find which is the impact that will break the material itself. So it's a specific machine. It's a very simple test. You can do it in some seconds. Of course, you will see some results about this. And we can analyze it in SIMULIA. So again, here we are applying the ductile damage model. Here the simulation, you can see in the middle, it's producing here the voids. So it's not on pause. The animation is very slow here because there are a lot of small steps, and now the break of the part. So it's producing the break that as we saw in the video. So here very interesting because we can see again the element removal inside the simulation, and we can appreciate which are the stresses. For example, here I can see the real stresses very near to an aluminium part, an aluminium yielding point. So very interesting approach for a nonlinear analysis. You can see the results very similar to the video. Here is another example. It's another zoom on also removing the top part to check which are the stresses on the top. Here it's another video on zooming on lateral portion on the sides of this Sharpie impact, and you can see this kind of notching inside, let's say, this portion here that is producing a very high concentration of stresses, and then the break that occurs. Very interesting model. So let's finish with this one. Also in this case I've applied the damage model, but in this case I've used the Johnson-Cook model. So here we are seeing a buckling, but a very complex buckling, because we are seeing the profile that is completely failing due to the compression load. And we can see the same results in the video. Very impressive to see in the simulation. So also here you can get other results as well. For example, you can see displacement again, and you can see the plastic strain. So again, in this case, I can evaluate which portions are failing and which are the plastic strain that I can see. Okay, so I'm ending this webinar. Again, I'm remember to you my GoToStage page. It's gotostage.com/channel/Alessandro Bellini. You can find other webinar on SIMULIA Structural Professional Engineer. Is the new name. Also now, I would like to have a final feedback from you, which is the level of interest raised by this webinar. Please vote. So again, some seconds to let all of you vote. Okay, so I can close the poll. Wow, I'm very pleased. Thank you very much. 100%. So thank you again. And also, I'm asking you if you want to be contacted for information about SIMULIA Structural Professional Engineer. So please vote. Okay. Again, some seconds to let you vote. Okay. I can close it. Okay. So here I've written my email. Also, you can go to my YouTube channel to see also SolidWorks simulation and flow simulation webinars from last year. So again, I'm open to questions. So please write your question. And I remember also to download, if you want, you can download the handout that I've provided in the panel. Those are basically some PDF, some white papers on how to evaluate those kind of hyperelastic Mooney-Rivlin model or the damage model and so on. Okay, I see some question about SIMULIA, how to connect to SolidWorks. Okay, yes, basically, as I said, there are specific webinars on this topic, but just to remember you, there is a specific connector from SolidWorks. It's a simulation connector you can use to basically to transpose, to deliver all the information that you have from the model, but also the boundary condition in the analysis that you have in SolidWorks simulation to the 3D experience SIMULIA. So all the work that you have can be transferred in a moment to the 3D experience, and then you can do this kind of analysis as you can saw in this webinar. Okay, there are no other questions, so okay, I can close here. Thank you very much for the participation, and let's meet on the next webinar. Bye, everyone.